Okay. So picking up with example 4. All right, let's go big here. All right. It says sometimes we may need to repeat ourselves. Sometimes we may need to repeat ourselves. All right. So if you didn't catch that, you could just rewind and put it on loop. Okay, let's try it out. The limit as x goes to negative infinity of x squared over e to the negative x. Never not first, direct substitution. If you plug in a negative infinity to x squared, what's negative infinity squared? Bless you. Right, where bless you is infinity. If you plug that into the bottom, because it's e to the negative x, and you plug in a negative infinity, you get e to the positive infinity, which is also infinity. So again, we have the quotient indeterminate form. L'Hopital's rule is one of our options. But as we just saw in example 3 at the end, because we're approaching some type of infinity and we have a quotient, we can just kind of look at the big O function and see which one grows faster. Which one grows faster, top or bottom? The bottom. We have an exponential in the bottom that goes to infinity, and the top is a quadratic, so again, it should go to 0. Let's try it or verify it with L'Hopital's rule, because you may not actually see that on an actual test, but you may say, L'Hopital's rule. So we're going to get 2x over negative e to the negative x. If you plugged in now, you're going to get negative infinity all over negative infinity. So it doesn't matter if you get plus or minus infinity quotient as long as it's an infinite over infinite quotient. So we can use L'Hopital's rule again. So notice we're making progress because the derivative for a power function kind of breaks it down. And if we do it one more time then, we're going to get 2 over back to e to the positive, just positive e, sorry, to the negative x. And now when you plug in, the top is always a 2. So as soon as you get like a numerator that's not a 0 or an infinity, you know it's going to work. It's going to be a definitive form. So we get 2 over what? Infinity. Now 2 over infinity is not a good answer, but it's not an indeterminate form. What is 2 over infinity? It's 0, right, because it's 2, and then the bottom is approaching infinity, which pulls the ratios down to 0. So on a multiple choice, that would be fine to leave it like that. On a free response, you're going to be like a cat, you know, when it does its business in the litter box. You're going to come back after you have 2 over infinity, and you're just going to kind of cover it up. Okay? Just cover it up. Because it's kind of like poop on a free response. College Board does not like to see 2 over infinity. So just cover it up. There you go. Oh, I covered up part of the 0. That's when the litter gets out of the litter box. There we go. There we go. Perfect. All right. Great analogies today. Sweet. So we did get 0. We verified what we knew to be true, but notice we did have to do 2 iterations of L'Hopital's rule. Sweet. Questions or comments on that? All right. Kitty litter. All right. The limit as x goes to 0. Oh, boy. Direct substitution. Square root of 1 is 1. 1 minus 1 is 0. 0 minus 0 is 0. Okay, so I get 0 on the top. Does that mean it's going to be indeterminate if I get a 0 on the top? No, because I could get something other than 0 on the bottom, which would be a determinate form. But alas, 0 squared is 0. So would this be a good candidate for RatCon? I got the square root of 1 plus x minus 1 minus x halves. That'd be like RatCon, right? It only works for 2 terms. We got 3 terms, so RatCon's not going to work. But what will work? Possibly. L'Hopital's rule. So let's lop it. Okay? So we get the limit as x goes to 0. Don't forget to rewrite the limit. Using the chain rule on the first term, we get 1/2, 1 plus x to the negative 1/2, times, don't forget, the derivative of 1 plus x, which is just 1. Bless you. Minus the derivative of 1 is 0. Minus x halves is the same as a half an x, so its derivative is a half. All over, the derivative of x squared is 2x. Now, we do want to clean up before we plug in. Notice that the 2 terms in the top both have a 1/2. So what I'm going to do is factor out the 1/2, and now multiplying by a half is the same as multiplying by 2 in the denominator, so that's going to become a 4x in the denominator. And I'm left with 1 over the square root of 1 plus x minus 1 in the numerator. So you could have left the 1/2 in the top. That's fine. But we want to put it into a version that is a little bit easier for us to evaluate. So now if we try direct substitution, we get 0 over 0 again. All right, so now I got to take the derivative of the top. So 1 over the square root of 1 plus x was pretty useful for evaluation purposes, but for derivative purposes, I think I'm just going to come back up here and write it as 1 plus x to the negative 1/2. Again, if you think well in terms of like negative fractional exponents, that's great. All right, so here we go. The limit as x goes to 0 using L'Hopital's rule again. We get negative 1/2, 1 plus x to the negative 3/2 times the chain rule, 1, and then the second term, 1, goes to 0. So that is it for the numerator, and the bottom becomes a 4. Now to clean that up, we get the limit as x goes to 0. In the top, multiplying by the half is the same as multiplying by a 2 in the denominator, so that becomes an 8. And then I'm left with a negative 1 over the square root of 1 plus x cubed. So you can leave it like that, or you could bring the square root of 1 plus x cubed to the denominator with the 8. There's lots of different ways to simplify that, but I prefer putting it back into radical form without a negative exponent for evaluation purposes. So this should be fine for direct substitution. In the numerator, when you plug it in, you get a negative 1 over 1 cubed is 1, square root of 1 is 1, so you get negative 1 over 1, which is negative 1, and the bottom is an 8. So however you simplified that algebraically, when you plug in, you do get negative 1/8. So this did require, again, 2 iterations of L'Hopital's rule, but it also required a lot of algebraic cleanup. And so these things could get messy in the intermediate, but after the cleanup, if you persist and you're not caught in an endless loop, you should get the answer. We knew that we weren't caught in an endless loop because if you notice, we were kind of making progress. We were eliminating terms in the numerator, which was good, and in the denominator, we were eliminating x's eventually. So that's progress. You'll see that you're getting caught in an endless loop because you'll have that deja vu feeling before, which means you feel like you've been there, and not the vujade feeling, which means I've never experienced this, okay? So hopefully you'll catch on. Now, I do want to do one last thing. Return to example 4a. If the denominator had been e to the positive x, direct substitution would then yield infinity over, when you plug in a negative infinity now, it would be e to the negative x. What is e to the negative x approaching? 0, because that's the same as 1 over e to the x. So direct substitution would give you infinity over 0. Is that an indeterminate form? Well, first, it's not 0 over 0, and it's not infinity over infinity. So it's not an indeterminate form, which means it should be determinate. So if you're ever faced with something like this, just remember infinity and 0 are whats of each other? Reciprocals. So if you want to bring the 0 to the top, that becomes infinity times the reciprocal of 0, which is infinity. And that's not indeterminate. That's going to be infinity. Or you can leave the 0 in the bottom and bring the infinity to the bottom, which makes it another 0. 1 over 0, remember, is some type of infinity. So either way, you get an answer of plus or minus infinity. So that's not an indeterminate form. It's got to be 0 over 0 or infinity over infinity. So if you get something that looks funky, you can just bring something to the other side by putting its reciprocal. Okay. Says be careful when evaluating one-sided limits. We've already evaluated a one-sided limit, but we did it on the calculator. So we don't really have to be careful because we're only approaching it from one side numerically. But if we're doing it analytically, we got to be careful. So when should we be careful? Always. Excellent. Always. So not just when you're evaluating one-sided limits, but let's say you're driving and you got a car in front of you with like plates from like Wisconsin, and there's a lot of heads bobbing around in there, and they are driving slow and stopping erratically, and it's raining and the streets are wet. You want to be careful if you're the car behind them, right? Leave plenty of space because they may just stop suddenly without notice in the middle of the road, and because the streets are wet, you may not have enough time to come to a complete stop, and you may just run into the back of them, and then it's your fault even though they're idiots. So just be careful. Yeah, that's just a, hypothetical situation that happened to Tate. So I could share that with you. 99% of good driving is looking out for the other idiots on the road that don't know how to drive. So if you think that you're a really good driver, you're a confident driver, maybe drive a little bit aggressively because you can handle it. No, it's other people you need to be aware of because they're the ones that don't know how to drive. Make sure you always have enough buffer space around you. So there you go. You're young, and so sometimes you get a little overconfident. So just be careful. Yeah, learn from others' mistakes so you don't have to have a $4,000 mistake yourself. Okay, all right. Anyway, we're going to be careful when we're evaluating one-sided limits. Never not first, though, direct sub. What sign of 0? 0. 0 squared, 0. All righty. Can we just analyze how fast the top goes with respect to the bottom here? It's a quotient. No, that only works when we're approaching plus or minus infinity. We're approaching 0 from the right. Okay, let's try L'Hopital's rule. The limit as x goes to 0 from the right. Now, because I told you to be careful here, it's kind of like you're expecting to get punched in the face at some time. You just don't know when, right? You're like, the derivative of sine of x is cosine of x. Anything wrong with that? I was careful when I did it. Okay. Derivative of x squared is 2x. Okay. All right. So far, so good. Try direct sub now. What do you get? Cosine of 0 is 1 over 0. What does 1 over 0 mean? Some type of infinity. Yes. Now, if this were a free response question, and they love to add these types of questions like at the last part of a free response, A, B, C, D, here's part E. What would be a safe and correct answer on a free response? D and E. Yeah, infinity does not exist. So you can put D and E and get it correct. But you would have to be a little bit more careful if this was a multiple choice question, because D and E are non-existent, as they sometimes type, would not be an answer choice. You would have positive infinity, negative infinity, probably 0, 1, negative 1, but you need to know which type of infinity it is, and you don't want to have to flip a coin in the middle of the AP exam, because you probably won't have a coin. So you have to raise your hand and ask Mr. Garnsey for a coin. Mr. Garnsey, can I borrow a coin? Oh, yes, you may borrow a coin. I've got all kinds of coins. What type would you like? I've got quarters, and I've got nickels, and I've got some pennies even. The dimes I've spent on phone calls, so I don't have those. Yes, you could give it back when you're done. Yeah, I trust you wholeheartedly. You wouldn't want to have to do that during the AP exam. So instead of flipping a coin, is it plus or minus infinity? Let's just keep Garnsey out of it. We're approaching from the right of 0. Go back to the original and just kind of remember, we did this before. Plug in a number just to the right of 0 and see what the sign is. Well, when you're approaching 0 from the right-hand side of sine, you can either think unit circle or you could think the graph of Sahala. If you're approaching 0 from the graph of sine from the right, what types of values do you have? Positive. And of course, x squared, you don't even have to think of the graph. If you're approaching 0 from the right there, you know because it's squared, it's going to be positive. So positive over positive is what? Positive infinity. There you go. No coin needed. All right, letter B. The limit as x goes to 0 from the left side of sine of x over x squared. That's deja vu, right? That's the exact same thing we just did over here. So we know it's going to be some type of infinity. I'm going to spare you going through the L'Hopital's rule all over it again to get 1 over 0. We know D and E is the safe answer on a free response, but now we need to know what type of infinity it is. So again, let's do the sine of x this time from the unit circle instead of the graph. Okay, so here would be 0 on the unit circle. If we're approaching from the left side of 0, we're approaching from quadrant 4. And in quadrant 4, we know sine is what? Positive or negative? Negative, right? So we'd have a negative number over, of course, x squared would be approaching from the left of 0 is still positive. Negative over positive is negative. Okay, now let's look at the interesting results of here. We plugged in and we got 0 over 0. 0 over 0 typically means there's a hole on the graph, right? Except for Jumpman, which is one of our parent functions. But this would suggest something different, right? If the limit from the right is infinity and the limit from the left is infinity, then guess what must live there graphically? A vertical asymptote. Yeah, so sine of x over x squared, even though it's 0 over 0, is an asymptote. So things get a little bit more complicated when you start looking at like non-typical functions. So this analysis kind of helps us determine that. Okay, so let's see. We've got a couple of minutes left until lunch. I don't think I'll start example 6, but we have time to read the intro into example 6. The rule. Which rule does that mean? That's a definite article. L'Hopital's rule / Bernoulli's rule. It works great, but again, it only works with one of these two quotient forms, 0 over 0 or any infinity over infinity. Of course, we know there are other indeterminate forms. We have seen 1 to the infinite power. That's an indeterminate form. We have seen infinity minus infinity. That's another indeterminate form. There are others that we haven't really seen yet. 0 to the 0 power is another indeterminate form. Infinity to the 0 power is another indeterminate form. So there are 3 exponential types of indeterminate forms, okay? 0 to the 0, 1 to the infinite, and infinity to the 0. The other indeterminate form that we have seen before, believe it or not, is 0 times infinity. Now, 0 times infinity is indeterminate because it's just a multiplicative version of 0 over 0 or infinity over infinity. Because if you bring the 0 to the bottom, you get infinity over infinity. If you were to leave the 0 in the top and bring the infinity to the bottom, you get 0 over 0. So infinity times 0 or 0 times infinity is an indeterminate form. And that one's going to be pretty easy to get into quotient form. We're just going to bring one of the factors to the bottom. So after lunch, we're going to determine then how can we get the other indeterminate forms, infinity minus infinity and the 3 exponential versions, how can we get those guys into quotient form so that we can use L'Hopital's rule, okay? That's after lunch. You can go to lunch.